Hello everyone. Today I will talk about two parametrizations of space groups. I call one of them the global approach and the other one the local approach. You're probably familiar with the global approach. If we want to describe a crystal structure, we can first think about what are the overall degrees of freedoms. You can separate the overall degrees of freedoms into two groups. One group are on the ASU, one group are on the unit cell. Let's forget about the ASU degrees of freedom for now because that's case by case. The unit cell degrees of freedoms are unique to the space groups. For the same space group, the unit cell degrees of freedom will be the same. And for all the space groups, there are up to 12 degrees of freedoms for the unit cell. And in general, they are the shape of the box, which are the length of the three sides, ABC, and the angles of the box, alpha, beta, gamma. The extra 6 degrees of freedom are the ASU location with respect to the box and the ASU orientation. Depending on the case, you might not have all those 12. Okay, so this is what I call the global approach, and all the textbook will talk about this approach because you basically need to know the whole crystal structure in order to write down these 12 parameters. Okay, let me go into a specific example to talk about the local approach. So take a P1 space group, for example. We actually don't have 12 degrees of freedom, we only have 9. Because for P1, we don't really care about the ASU location. You can shift the ASU in any way and it will be the same unit cell. Okay, in that case, what would be the local approach? It's very obvious. That will be 3 translations. And these 3 translations, they're just 3 vectors, and they are different from this global parametrization, but you can easily do the mapping between the global one and the local one. The length of the 3 vectors corresponds to ABC, and their relative angles defines alpha, beta, gamma. And the ASU orientation will be given by your starting structure. If you start with a specific ASU, that will define the ASU orientation, and that also defines where the concrete ABC vectors in space. Okay. Let's also go through the P-1 example. Now you will have 12 degrees freedom. So besides the ABC vectors, just like the P1 example, you will also specify where the inversion center is. You have to specify the one that's within the unit cell. So that will give another 3 degrees of freedom. So in total there are 12. Okay, hope this is helpful.